Okay, so in lab this week, we're going to focus on the experimental technique of calorimetry. Now, calorimetry is just simply a process where we measure the heat released or absorbed by a reaction or process. We're going to focus on the reaction of an acid and a base, sodium hydroxide, our base, hydrochloric acid, our acid, and we're going to look at the heat released or absorbed during the reaction of those two. Now, there's various different steps or processes that we can do when we're looking at these three different reactions. And we're going to complete these reactions in a coffee cup calorimeter. Coffee cup calorimeter is very simple. We have a coffee cup. We're going to put a thermometer in there. Then what we'll go ahead and do is we'll put a stir bar in here, and that's going to make it so that our solution is well mixed. And that means that whatever temperature our thermometer is measuring is hopefully the temperature of the whole solution. Okay. So we'll go ahead and we'll start with our solution in here, and maybe we have our hydrochloric acid in here, and into that we can add our sodium hydroxide. Now maybe in this one reaction we look at our sodium hydroxide solid, and so the reaction that we'll have is solid sodium hydroxide, hydrochloric acid, and that's going to produce water and our salt, sodium chloride. Okay, so when this reaction happens, what we want to do is we want to determine what is the enthalpy of this reaction. Is heat evolved or is heat absorbed when this reaction occurs? Well, in order for us to do that, we can't just simply take an enthalpy measurement device and measure the enthalpy. We're going to measure the heat. Now, we're going to look at that by the change in temperature of our solution. Okay? So we're going to be able to calculate the Q of our solution based upon the fact that it's going to undergo a temperature change. Okay, and so we have to identify what this temperature change is. And we're going to have to look at the specific heat of our solution. Now we're going to be using water as our solvent. That's going to be the majority of the solution. So we're going to be able to use the specific heat of water because the majority of what was actually changing temperature in here is the water. Okay. Now, if we look at the mass that we're going to be using for our solution, we're going to need to have the total mass of our solution. Well, in this case, that's going to be the mass of our sodium hydroxide plus the mass of our hydrochloric acid solution. Okay, so we can have we'll have a mass of both of those, and the total mass is what is actually going to change temperature, either increase or decrease in temperature. The final piece is our change in temperature. Now in class, usually you're just told the initial temperature was X, the final temperature was Y. You could easily calculate the delta T. Well, here we're going to have to experimentally determine our delta T. And in order for us to do that, we're going to get a graph. Okay, and we're going to look at our change in temperature over time. Okay, so we'll have our time here, we'll have our temperature, and before we add in our sodium hydroxide, we'll get a baseline. Okay, so we'll have our initial temperature that we would measure. Now at some initial point, what we'll do is we'll add in our reagent. Okay, so let's go ahead and say we add in our sodium hydroxide at this point. We're going to start to get a reaction to occur. Now if this is an exothermic process where it's releasing heat, we're going to see that our temperature should go up. So our temperature will increase. At some point it's going to max out and then slowly start to decrease. Okay. Now, if this was a perfect insulator, our temperature would rise up and then remain constant. Well, since this is not a perfect insulator and the outside is cooler than the inside, we're going to slowly get this drop in temperature. But we need to account for that kind of loss of heat to the surroundings as our reaction is happening. So we can extrapolate. We'll see that this is going to be fairly linear. What we can do is we can go ahead and extrapolate this graph or curve here until it reaches what would have been our initial temperature. Okay, the place that we added in our sodium hydroxide, the reaction place. Okay, right here, that temperature where those two lines meet, that is what we're going to call our final temperature. Okay, so now we'll have our final temperature, we'll have our initial temperature. We can go ahead and calculate delta T. The final step is going to be determining our Q of our reaction. Okay, and we know that the Q of one piece is equal and opposite to the Q of the other piece, right? If something loses heat, something else has got to gain it. So then this is going to be equal and opposite to the Q of our solution, which gets us to the Q of our reaction, which we can then go ahead and use to calculate the enthalpy. Okay, now remember, the final step is that we're going to have to take into consideration that we want to measure that per mole. Okay, and so I'll let you work on that in lab and figure out how we can actually accommodate for the fact that maybe we didn't react 1 mole of each of these. And how would we determine the delta H per mole based upon the Q of our reaction that we calculate from our temperature change.